this conference 2 years ago, and I had a lot of fun, so I was very happy to have the opportunity to visit you again. Also, I caused some trouble with my travel plan, so thank you for taking care of everything. So this will be a talk about the micromechanics of the yielded transition in granular media. So we are coming back to systems that are out of equilibrium with our preferred game, which is breaking things, and try to understand what's happening. And of course, the important question, the question that you have is that how this kind of phenomena occur. And these are, you see on the top row, they are just images of landslide, and on the bottom one, there are some pictures referred to earthquakes. So this is the general framework. But of course, I am a theoretical physicist, so I'm going to be far away from reality, from these things, and we're going to focus on simple models. The rational, what is it, is that this thing is very difficult to be understood, and in general, not things that you can reproduce in the lab. So what you try to do is to develop simple models and try to understand them. Well, if you succeed, then you might try to complicate things and to move towards reality, of course. So what I'm going to do is the following. This is the plan of the talk. First of all, I would like to tell you something about the instability of what I'm calling a molecular solid. And essentially is what you can say about the stability of materials, how the materials break, when you can write out an Hamiltonian. So this is, for me, means molecular solid. So you have an energy for this function. And so this energy is going to depend on the deformation you're applying to the system, and at some point something is going to occur and the system breaks. So what's going to happen? Then I would like to convince you that when you deal with granular system, actually you cannot write down an Hamiltonian, and we're going to see why. And because of this, you cannot use these theoretical tools that have been somehow well developed, and you need to come up with new ideas. And I'm going to review two approaches that have been somehow suggested in the literature. One is say that, well, a failure like this is actually originated by a localized event that occurs at the level of the contact between two particles. And another one is telling you, well, actually it's also possible that you have some event that is collective, so it's characterized by the cooperation of a large number of grains. So you have a length scale here that grows. And see what's happening. And in these things, I'm going to review some numerical results that actually points toward the existence of this collective approach. But so far, this result that are also now not really brand new, were lacking of a real theoretical interpretation. So there is a collective failure process, but what is it? And finally, we're going to show some novel theoretical results that are essentially taking this theoretical framework and they are modifying it to describe systems that are not an Hamiltonian. And we're going to show that it is possible to do so, and the result is a new kind of bifurcation, a new kind of dynamical instabilities that we're going to call oscillatory instabilities. And then we're going to numerically investigate it, so to check some of the theoretical prediction numerically, and then we're going to also describe the experimental relevance, the possible experimental relevance of this approach. So first of all, let me start saying something about how a Hamiltonian system fails. And we're talking here about, usually we focus about amorphous systems. And essentially I'm going to review these works that are 20 years old by mainly Malandro and Lux, and then there is another quite relevant paper by Craig Maloney and Annie Lemaitre. And essentially what is the idea? Well, we're going to focus on systems that they emit an Hamiltonian and they are at zero temperature. Zero temperature for us doesn't mean 0 Kelvin. Zero temperature means that thermal fluctuations are negligible. So this is does it mean. And the system is admits an Hamiltonian, so we can write down the energy of our system. That is something like this. So sum of the interaction potential between all pair of grains. And these things depends on a constraint. Could be the extender boundary condition, like for instance the strain gamma you applied to your system. You deform the system, so the strain is imposed by you, or could be some external stress. So this is one feature, and then this means that we have an Hamiltonian. We are allowed to write down this object, and this is going to govern the evolution of the system to Newton's equation of motion. And the other thing is that we are neglecting thermal fluctuation, and this means that the system is always trying to be in a minimum of its energy landscape. Is minimizing the energy. So if this is like a schematic picture of the energy landscape, you have to think that your system is always in a minimum. So what's happened when the system is in a minimum? It means if you kick the system, the system is going to oscillate a little bit around its minimum position. And how can you characterize these things? Well, you characterize with the curvature of the minima the system in. Okay, so this is a cartoon in one dimension. If you want to be formal, what you have to do, you do so-called normal mode decomposition. So you take your system and you write down you evaluate what are the normal modes. So if you are in 3 dimensions, if you have n particles, you have 3 times n modes. These are independent orthogonal direction of oscillation, and each mode is characterized by an eigenfrequency omega. And how do you get this mode? Essentially, you just solve for the stability matrix associated to the linearized equation of motion. So essentially, you write down what is the Hessian matrix, which is the matrix of the second derivative of the energy with respect to the particle position, and you diagonalize this matrix. So when you diagonalize this matrix, the first thing that you notice is that this is a real matrix, and it is also symmetric because it's a matrix of the second derivative. And so you know that all the eigenvalues are real. And what is the interpretation of this eigenvalue? Well, these are the square root of the eigenvalue are the omega, the frequency of oscillation in the different minima. So what is the physical interpretation? The physical interpretation is the following. If you have a system that is in energy minimum with some value for the coordinates of your system, and you slightly displace the system along the direction of an eigenvector, ui, with associated eigenvalue lambda I, there will be a change in the energy. So you're moving a system in a parabolic potential. What is the change in energy? Would be this one is connected to the eigenvalue, or if you want to omega square. So you see that you have 2 possibilities. Either all the eigenvalue is positive, so omega square is positive. So this means that this is the situation that you have. You are in the minimum of the energy potential, so you displace the system and the system tries to go back. So in this case, this mode is stable. Or the other possibility is that this is negative. So in this case, the system is unstable. You kick the system and the system starts flowing. So if you have a system and you see it as a solid that is stable, it means that all of the normal modes have this feature. You are stable in all phase space directions. So what was the physical picture is that, well, these modes, they actually depend on the boundary condition, on the strain that you are applying to your system, to the deformation. So at some point, is it possible that one of these eigenfrequencies is going to 0? So you start from a stable state, so all the eigenfrequencies are positive, and then you slightly deform the system, the eigenfrequencies are changing, and one of them can hit 0. So when it hits 0, it means that a minimum is becoming a flat, so it's becoming a saddle point. So this is a saddle bifurcation. And when this occurs, the system can move along one direction of phase space, the one associated to this eigenvector, and it doesn't found any mechanical resistance, so it's free. So the system is unstable in this direction. So this is something that is somehow well known in the literature and been validated in a number of papers. And this is just a paper from one of people that have investigated this thing, which is a paper by Lisa Manning and Andrea Liu. And so they have a system of particles in a box, and they are doing the so-called quasi-static deformation. So the system is there, they minimize the energy. Then they increase slightly the strain and minimize the energy. Then they increase the strain and minimize the energy, and so on. So the system is moving very slowly. And you can measure the stress as a function of the strain. And what is doing the stress? Well, it's growing as you deform the system, and then at some point you have a drop when the system fails. So these vertical lines that you see here, they correspond to strains at which they see drop in the stress. So the system fails at this value of the strain. What they're plotting here, so at every value of the strain, after the minimization, they compute the Hessian matrix and the eigenvalues. And so they are plotting here just the smallest eigenvalue of the system. And what they found, well, they found is that as the system approaches failure, you have one of the eigenvalue that is really going to 0. So this is as predicted by this theoretical framework by Malandro and Jacques. And another interesting thing that you can actually see is that you can show that this divergence, this is a critical behavior, not a divergence, that goes like the square root of the distance over the critical point. So this, theoretically, it opens the possibility of some prediction of failure, because if you look at the system and you find that the system is, an eigenvalue is behaving as a square root, then you may perhaps estimate the critical value of the strain. Of course, this is just a critical behavior that is occurring very close to the transition point, so from the practical point of view.
So is this only true when you have harmonic potentials? Because
No.
You cannot do a eigenfrequency decomposition, then what do you think? If I cannot recognize the matrix for
Well, you're doing a stability analysis. So you start from the equilibrium condition, and then you perturb the system, and you stop to first order. So this is the definition of the normal modes, right? The normal modes are defined whatever potential S. It's just the harmonic approximation. So yeah, so you're making a harmonic approximation for the deviation, as usual for the normal modes. Yes.
So this is a technique to identify the failure point, right?
This is. First of all, you understand what is occurring a failure. So here, you understand that failure occurs when one of the eigenvalues goes to 0. So this is the first thing you understand. Then you may think, okay, now I understand this point. Can I use it for making prediction? Well, in theory, yes, because if you are here, you look at the eigenvalue, so the system has not yet failed, but you can see that this behavior, this object is somehow critical behavior, so you can make a fit and try to extrapolate. Then the practical relevance of these things, of course, is questionable because in experiment it's not that easy to get the modes and to make the fit. This is a critical behavior, so it's just very close to the transition point. So it's not clear that this is really useful, but at least you understand what's going on.
Why in the model the eigenvalue then is recovered again as it goes up? So there are some failure, but then I see that the curve goes up. The vertical line.
This one?
Yeah.
Oh, this is it's just the vertical line. It's just a line that indicates the critical values, a gamma C. So you see, you have one gamma C here, and you have a critical mode, and another one gamma C here.
But if you keep straining, then what?
Here you have a rearrangement. So after you release the avalanche, you will go again in a steady state.
This can be a small rearrangement.
Could be, yeah. You don't know anything. It's an over problem. Yeah, you don't know if it's a macroscopic failure or it's a failure. You have a drop in the stress.
But in any case, I mean, this kind of models, you will have avalanches, but then again, as you're driving, again the elasticity will develop, and again it develops.
Yes. So it's a stick.
What happens that you start at that point on the right, no? The same mode then?
Then the same mode will be another mode. The system, the configuration changes. So all of the.
It's not the same mode.
Yeah, all of the modes can be different. Okay. So. You have so if you the typical curve that you have when you do this kind of things, this kind of experiment is a stick-lick curve. So you have as a function gamma, and for instance the stress, and what you have is you are going to have a linear regime, and then you start having at some point all the drops, and you go in a steady state. So it occurs in principle all value of the strain, but usually you do not have a very, very small strain. So you drive the system towards, but it depends on the parameter or the volume fraction and these kind of things.
So gamma C is not 0?
No, gamma C is not 0. This is like, no, gamma C, you have a kind of stick-slick experiment, like earthquakes. So every some time you have a failure, right? Okay, so this is the picture for the people succeed developing for a Hamiltonian system. So now the first thing I'd like to clarify is that this picture cannot work for granular system because you are lacking an Hamiltonian. So what I mean here is the following, that of course if you have a bunch of grain in a box, you can write down the Hamiltonian in terms of the degree of freedom. But the degree of freedom that you have to consider are just too many. They are the position and the momentum of all the atoms of all the grain. So you should develop a microscopic description. And this is not what you want to do because you are essentially too many degrees of freedom. So when you deal with this kind of system, you want to develop some kind of effective model and to keep track just of what you think are the relevant degree of freedom, which usually are taken to be the position and the momentum of the center of mass of the particle. So this is the only thing you want to care about, right? And also the angular position because the particle can rotate, for instance. So you define this coarse grain degree of freedom. And then these coarse grain degree of freedom are going to interact in somehow. So you need to understand what is the typical interaction between this coarse grain degree of freedom. And how do you get interaction? Well, you essentially formally integrate over the microscopic degree of freedom to end up with an effective interaction only dependent on the position and the momentum of the particle. You can do that. And at the very end, what happens is that you end up with some effective forces between the degree of freedom, so between the position of the particle. And the key point is that these forces, you cannot write them like this. They are not the gradient of an energy. So this means that these forces, they are not originated from a potential. So you don't have an Hamiltonian description. And there are different ways, there are a bunch of different models for the interaction between grains. And this reflects the fact that when you do the coarse graining, you may adopt different strategies. But whatever approach you use, this is always true. You can never write down the force as a derivative of the energy. And we're going to see in a moment why. So what is the conclusion is that this somehow nice theoretical framework, which is suggesting that you have an eigenvalue that goes to 0, just does not apply because you don't have any Hessian matrix, because it's the derivative of the energy, but you don't have any energy. You cannot write the energy of the system. So why you don't have an energy? So this is true, as I said, for all interaction model, but I just want to use an example, which is the Hertz-Mindling model, which is, I guess, right now the standard. Everybody is using this one in theoretical and numerical studies. So you have two particles, and what is the force between two particles? Well, first thing, if the two particles overlap, you're going to have some normal interaction. So, of course, what does it mean overlap? What is this delta? This delta is just a parameter that tells us that there is some deformation at contact. You don't have real overlap between the particles. It just tells you it's a way to measure the deformation of the particles. And you are going to have a normal interaction, so along the direction of delta, which is just delta to the 3 half. This is the standard S model. And then you may have also some dissipative term that depends on the rate at which the particles are approaching. So you have a normal component for the interaction. And then you have a tangential one. So if particles translate one to respect to each other, you can define this translational displacement. So this translational displacement, the animation is done with particles that are moving like this, but this is also there when particles are rotating one to respect each other. So what is this object, this t? This is just the integral as a function of time of the relative velocity of the particle at the point of contact. So the particles are sliding one to respect each other, either because they are moving like this or because there is sliding associated to the rotation, relative rotation of the particle. Okay? And what is the expression for this tangential force is usually the Mindling force, which is this one. So it's a spring with, so it's proportional to t and with a minus, but with a stiffness that is k, some constant, and delta to the 1/2. And of course, these forces are not Hamiltonian because you have dissipation. But you may think, okay, I want to describe a quasi-static condition, which dissipation is not there, so you can neglect dissipation. And even if you neglect dissipation, what you find is that the derivative of the force with respect to x, or the force along x with respect to y, is not equal to the derivative of y with respect to x. So these forces are not coming from a potential. And the reason is physical. It's not just because we are making something fancy. It's physical, and it is in this delta to the 1/2 in the tangential force. What is this delta meaning? It just meaning is a measure, this delta 1/2, of the area of contact between two objects that are two spheres that are pressed one to respect to each other. So you expect the tangential force to depend on delta, because the tangential force will be larger, the larger the surface area of contact. So there should be a delta dependence here. And this is creating the trouble. Okay, so I would say that you are missing this theoretical argument based on the Hamiltonian. So what you can do, what you can say about the failure, and I want just to say two things that have been somehow suggested in the literature. So the first thing is that when you look at the force, apart from what I've been telling you, there is another point, which is, as you know, the Coulomb law. So you have a normal force, you have a tangential force, but there is a relation between the two, because the magnitude of the tangential force cannot be larger than the magnitude of the normal force times some value of mu or the friction coefficient. So if you plot the tangential force as a function of the shear displacement between the particles, you see that this is growing, but at some point it hits its maximum value. So what's happened to a contact when it hits a maximum value? Well, somehow it's free to slip, because you don't encounter any increasing resistance to the relative motion of the particle. So one speculation was the following. So consider, for instance, this drawing, which is a drawing of a packing, in which the line here represents the normal force acting between two particles. So the larger the line, the larger the force. So what could happen is that you are slowly deforming the system, and at some point, one of the contact reaches the Coulomb threshold. So this contact reaches the Coulomb threshold. So what's happening afterwards? Well, you have two possibilities. Either, for instance, something small happens, so few other contacts that are close by reach the Coulomb threshold and then everything stops. Or the other possibility is that you have a propagation of failures that span the whole system, and this makes the system unstable, and the system starts moving. So this is one proposal that was somehow investigated a lot in the context of avalanches. So you have grains on a plate, and then you increase the tilt angle. At some point, the grain starts flowing. So what's happened when it starts flowing? And this was the suggestion. So in this approach, the macroscopic failure is triggered by a localized thing, which is a given contact is failing because it reaches its Coulomb threshold. And this, in an avalanche process, is triggering the macroscopic failure. There is also a complementary approach, which is also more from the engineering community, which is, they call it second word criterion, which try to see the instability again as a bifurcation. So they say, okay, if I have an instability, it means that when the system is stable, the kinetic energy of my system is small. Then when it's unstable, the kinetic energy steeply rises. So the question is, where is this kinetic energy coming from? So what they say is the following. Well, what's happening? What is the variation of the kinetic energy? Well, if you consider that you're slowly deforming the system, you are doing some work on the system, which is the one. That is work that is usually done at the boundary because you are deforming the system. And how is the system responding? Well, it's doing some work itself, and this work you can express as just the stress and then the change in the strain field. So what they say is that, and this is what they call the second order work. So what they say is that, well, the system might become unstable because is it possible that this second order work vanishes or also becomes negative? So essentially, you are giving energy to the system because you are straining, but the system is not able to store this energy doing some deformation. So it's also possible that the system is actually doing some work itself on the outside. So where is this work going? It's going to the kinetic energy. So when this object goes to zero, you may have a kind of bifurcation. This is what they are arguing. And you see, this bifurcation, this approach is not making any reference to the Coulomb condition. So perhaps this bifurcation occurs when you have when a contact reaches the Coulomb threshold, but perhaps not. So there is no reference for that. So at this point, I'd like to show you some numerical results that we have done with Lucilla, the Archangelis, and others that essentially try to look in very minute detail at the failure of a model system to understand if when the system fails, you have a contact reaching the Coulomb threshold. So is it true or not? And the model we are using is a model that somehow is based on somehow, the idea was to develop a model that can vaguely mimic earthquakes. So, you know, earthquakes, they occur along persisting fault, and in between two faults, you have granular materials that are just pieces of rocks, which are crushed rocks between the two planes. So how do you model this one? Well, there are a variety of different models. So what we do is the following. We have a granular particle, which are these gray spheres here, that are enclosed between two rigid plates, which are these red plates. And then the two plates are kept at constant pressure, P. And then the bottom one is fixed. The top one is driven. It's driven with a spring mechanism that is the usual driving approach that you use to reproduce as stick-slip dynamics. So essentially, if the system is not moving, it's jammed, then the length of the spring is increasing linearly in time. So the stress that you are applying to the system is increasing. So you're driving the system towards failure. At some point, the system fails, so it starts flowing. So at that point, the plate will start moving very quickly. And so the length of the spring decreases. And so the stress applied drops. And so the system now is at a smaller applied stress and can jam again. And then these things repeats over and over and over. And so you have typical stick-slip dynamics as I draw it here. So of course, what you get depends on the control parameter, which the main one here are the pressure and essentially the velocity, which controls the rate at which you give energy to the system, the stress rate, and you find what you expect. So if the velocity is very high and the pressure is very small, then the system is in a state in which it flows continuously. Vice versa, if the velocity is small and the pressure is very high, you end up in this stick-slip dynamics. And this is what we are going to focus. So you can, for instance, have a look in this plot at what is the position of the top plate as a function of time. So what you see is that the top plate, it looks like it is not moving, and then all of a sudden the system jumps, and you have a jump in the position of the top plate, and so on and so forth. But actually, these are not the jumps you are interested in, because if you look, you zoom in one of this area, what you find is that this plateau regime has actually made of different smaller jumps. So you can make the statistics of the jumps, about how much the system is moving every time there is a jump. And what you get this distribution here, so a power law distribution with a hump. And the power law distribution and the exponent was somehow reasonable in the earthquake community. So this is what you find, and then you may think, okay, are these results robust with the model parameter? And this is where we show that they are. So you can change the thickness of the system, and the exponent is not changing much. You can change the length of the system, and you see the only thing that changes is the position of the bump. So if you rescale your slip by the system side, all the bumps collapses. So this tells you that this bump is a finite size effect, it's not what you care in your system. And then you can play with friction or with the inertia of the particle, whatever you want. And you see that the distribution is somehow robust. So say, okay, I'm capturing an emergent behavior of my system. Okay, so this is the model, which is somehow mimic the earthquake physics. And now our question is how a failure is occurring. So this is how a stress versus time curve looks like. You see, you will have different failures. This is not in scale because the slip is essentially is a vertical line, right? Because it's very fast with respect to the loading, which is not as shown here. So what you want to do is to understand what's happening when the system is failing. So the first thing you want to do is to understand and to locate this TF with a very high precision. So then you can zoom on the system and say, okay, is there any contact reaching Coulomb threshold at that time, or what's happening at that time? So this is what we have done. And how we have done this thing, of course, you exploit the power of molecular of numerical simulation. So you take your system and you make a replica at some time, and then you follow the evolution of the system after switching off the drive. So there is still the spring, but the spring is no longer increasing in time. The length of the spring is fixed. So you have essentially two possibilities. Either you make the replica during the stick phase. So here the system is solid. So if you make the replica and you follow the evolution without further increasing the applied stress, the system stays solid. So what's happening is that if you look at the stress of any other quantity, it's not changing. The system is solid. The other possibility is that you made the replica in the slip phase. So if the system is in the slip phase, even if you are not driving it, it's going to move. So if you look at some whatever dynamical properties you want, the drop in the stress, mean-square displacement, you're going to see some signal. So by doing that, you can then move some splitting algorithm to locate the location of the failure with a very high precision. And what we do, we locate it with a precision which is the highest we can have, which is that of our integration time step. So now we know precisely when the system is failing. And now we can go back and zoom and say, okay, now what's happening when the system is failing? And this is what is shown here. So what I'm plotting, so this is, again, the fraction of contact that fails as a function of time. So this is our estimator for the failure time. You see that you have an increase. So this is a large event because all of the contact fails. But then if you zoom in time, you see how many contacts reaches the Coulomb's threshold as a function of time. What you see is essentially is at 0. Then you cross this vertical line that marks the time at which the system fails. And then afterwards, contact reach the Coulomb threshold. So the message is the failure is not, for these cases, is not driven by a localized event. What's happening is that first we have some collective process. Particles start moving. When they start moving, some contact reach the Coulomb threshold and breaks. So you do have some collective process. There is another indirect evidence of the existence of a collective process that comes from the investigation of the response to perturbation. So if the failure is associated to a localized event, like also a discontinuous event, like a system reaching the Coulomb threshold, then the system has no knowledge of the fact that it's approaching failure. So the mechanical properties are not expected to change as you approach failure. So what we have been doing is, again, consider different small events, and we have investigated the mechanical response as we approach these events. And what we have been doing is the response to some perturbation. Don't want to give details, but here is the response function. So essentially, we have the system and we kick the system and see what's the response. And what you see is that the response function is actually increasing towards as you approach the failure time. And then the system fails, and then you have an increase as you approach the failure time. So this tells you, okay, there is something that is cooperative beyond. There should be some kind of length scale. There should be something that is growing. And so this is not compatible with the idea that the failure is just originating from a contact that is reaching Coulomb. There is something that is collective. Okay, so this is the status. But there is something that is collective. There is some numerical evidence, but what is it? And this is some recent piece of work I've been doing in which we try to generalize this Hamiltonian approach to describe the failure of non-Hamiltonian system. So first of all, what are the equations of motion for our particle, neglecting dissipation? These are just Newton's equation of motion, and here we just have a tilde, just to remember that our degree of freedom could be either position of rotation of the particle, and so the masses will be either real mass of the momentum of inertia, and similarly the force is either the force or the torque. And you can look at the linearize this equation to study stability, and you find that the stability is essentially determined by the properties of a stability matrix, which is just minus the derivative of the force with respect Jacobian derivative of the force with respect to your degree of freedom. So how this relate to the Hamiltonian case? Well, it's easy. So you see in both cases you have minus the derivative of the force with respect to the coordinates, so the same thing. But in the case of the Hamiltonian, this derivative of the force are originating from you. So you know that your matrix is symmetric. While this is not generally the case when the force is not coming from an Hamiltonian. So what you're going to have is this general case. So this means that your stability matrix will be real matrix, but in general will not be symmetric. What does it mean, not symmetric? It means that when you diagonalize, in general, you're going to have a complex eigenvalue. And of course, you say, okay, but everything is real. What does it mean to have a complex eigenvalue? So we have some problem with complex number. We were discussing at dinner yesterday. So here, everything is somehow clear. So suppose you diagonalize the stability matrix, and you have a set of eigenvalues, this one, and some of them will be imaginary. Okay? So how can you interpret them? Well, actually, your non-symmetric matrix admit another decomposition, which is not diagonalization, which is a block diagonal diagonalization. So this is the block diagonal. So each element on this here, here will be either a scalar or will be a matrix. And essentially what's happening is that if you find, when you diagonalize, you find that an eigenvalue is real, then the block is actually a 1 by 1 block, so it's just a number, and it's exactly equal to the eigenvalue. If instead you have an eigenvalue which is imaginary, you will show that another imaginary eigenvalue will be its complex conjugate. Both of them are eigenvalues. And this gives rise to a block which is a 2 by 2 block of this kind. So you can write down your imaginary number as some amplitude times the phase, and your block 2 by 2 block is this object here. So what is this? It's a rotation matrix of the angle theta times some amplitude lambda. So you immediately understand now what's the feature, no? Because usually when you have an eigenvalue, you're just multiplying the object by the eigenvector, by the eigenvector by the eigenvalue. This is what's happening. So what's happening here, if you have some directional phase space, you are rotating the vector in phase space by an angle theta, and then you are scaling the length. So this is a rotation scaling matrix. So this is the meaning. Okay, so the upshot of the discussion is that if you follow the evolution of the system, when you have complex eigenvalue, the two complex eigenvalue, they give rise to solution of this kind, in which any perturbation Q0, as it grows with amplitude which is like this, and then it's also oscillating this other way with sine omega t. So notice that if you have a complex eigenvalue, you also have the complex conjugate. So if you have an omega I which is positive, you also have an omega I that's negative. So as long as you have a complex eigenvalue, you know that you will have a growing perturbation omega positive here. So the perturbation, the system is going to be unstable. But the perturbation has this unusual feature. So the perturbation is growing, oscillating, and omega I, the imaginary component, is setting the growth rate, where omega R is setting the frequency of oscillation. Okay, so this is the theory. Can we make any validation of this? And this is what we have been doing. What is the numerical model that we have considered? Is essentially the Hessian-Mindley model I've discussed before, but we have with a little catch. Because what we need to compute is the stability matrix. So we need to make the derivative of the force with respect to the coordinates. And if you look at the Coulomb's law, you find here a cusp. So here the derivative is not well defined. So what we have been doing is just make the simplest modification you can do to smooth out the Coulomb threshold so that the derivative are well defined. So when you have done this, we have diagonalized and studied what's happening. So we have a system of disk, and we made this kind of investigation. And we're going to consider two kinds of dynamics. The first one is an overdamp dynamics, which is as follows. We have our system, we strain it, so we change the strain by a small amount, and then we use some this Newtonian dynamics with a damping force to somehow relax the system. And the damping force is very, very high. In particular, the time scale is much higher than the time scale associated to the propagation of sound waves. What's the key point here is that we're saying that the system might be unstable. So if we don't dump the energy, the system, we are never going to see the stability. The system is going to move until it goes to a steady state. So if you want really to drive the system in a state in which, when you diagonalize the stability matrix, you need to find a complex eigenvalue, you need to drive the system in a state where it actually is unstable, the system doesn't like. So what you can do, you add a huge damping, so that essentially you are preventing the system to move. And this is what we are doing. Then, this way we can drive the system and actually see a system that is unstable, preventing the developing of the instability. Then if you want to see the instability, what you do, you just neglect the damping. So you have just Newtonian dynamics. So now you have a system which is unstable, and there will be some also small numerical perturbation, numerical noise, and this will be amplified and should give rise to this oscillatory instability. Okay, so this is what we are predicting. And this is some result in which we just focus on a pair of complex of eigenvalue, a function of the strain. So again, we increase the strain by a small amount, and then we not minimize, but we do this overdamp dynamics to try to relax all the kinetic energy. What you see here, you find two eigenvalues that are real. So here the system is stable, that are real, this one and this other one. You see that as a function of the strain, so this is the real component of the eigenvalue, and this is the imaginary, so this is 0, so this is a real eigenvalue. And as you strain, you find that these two eigenvalues, they are actually colliding at some point. So at this point, the real part of the eigenvalue is the same, and what's happening is that the imaginary part starts to be opposite.
So just an operational question. So if you are forming, you are dissipating, and then you are computing.
Yes, this thing. So what you see here the collision between two eigenvalues, two real one, that gives rise to the birth of two complex conjugate eigenvalue. Now they have the same real part and opposite imaginary component. And here what you see just the scalar vector of the eigenvector associated to this eigenvalue. So if these are complex conjugate, then also the eigenvector should be complex conjugate. And so when you compute the scalar product, it should be 1, and this is what you find. So you really, it's just to see. And what you see is that here you have some this collision, and then as you keep straining the system, actually the two eigenvalues can depart at some point. And what you can actually do, I'm not showing the theory, well, actually you can show what is the rate at which of collision. So you're looking as a function of the distance from the collision point, you're looking at the distance, at the difference between the eigenvalues. And you find that it exhibits a critical behavior with scaling square root. And same thing for the departure. And this is something that analytically you can actually predict. Okay, so far we have studied this dynamics, which is overdamps. So the system is unstable, there are complex eigenvalue, but the stability is prevented because the system is overdamped. So now we have a look at what's happened when we eliminate this overdamping. So it's purely Newtonian dynamics, Newton's equation of motion with no damping. And this is what you find. So we have a configuration in which there are some set of complex eigenvalue, and you look for the evolution. So you can see that since the degree of freedom are oscillating with omega I sinus omega r, the mean square displacement is related to the square. So it's expected to grow with 2 omega I t sinus square. And you look at your eigenvalues. You look for the eigenvalue with large value of omega I. That will be the one with the largest growth rate that you expect to dominate. And this is the prediction that you have, the red one. And these are the blue one is the numerical result. So you see that, yes, I do see this exponential growth. At short times, you don't see it. Why you don't see it? Well, because of course the dynamics will be dominated by high frequency mode, the system, but these are stable. So it's like when you see the mean square displacement of a solid. It grows and then reaches a plateau. These are just high frequency, all the vibration. So on top of this vibration, you do have a mode that actually is diverging, but this set in just after some typical time scale. So this is what we observe. Then if you zoom on a very short time scale, which is much shorter than the time scale set by the frequency, so that you can neglect this exponential growth, what you see actually the mean square displacement is oscillating. And the oscillation have a typical frequency, which is the one you predict from your eigenvalue. So this appears to work. And it's also nice to see what are the particle trajectories during an oscillation, an instability. And these are the particle trajectory that you see as a function of time. And I have to say that these are not the actual particle trajectories, but they are scaled by a factor 10 to the 6. So really the trajectory, they looks like points, and so they are quite. So what you see, well, the particle is drawing some spiral, growing, and it is fine because we have seen that the complex eigenvalue is represented by this block scaling matrix. So there is a scaling factor plus a rotation. Scaling factor plus a rotation is clearly leading to a spiral motion because it rotates, and then the length of the vector is increasing as a function of time.
And here you're showing only those contacts which are over.
No, I'm showing everything. These are all contacts because this is collective. I'm showing the evolution of the system. These are all particles, right? Because I'm showing all particles. Just the only thing we're doing is that the spiral are actually very tiny. So I'm just rescaling by 10 to the 6 the size of each spiral. Otherwise, you don't see anything. Okay, so far so good. But the only thing that we were able to do is to somehow identify the extent of this new instability and to make some prediction in the linear regime. So at some point, the stability is going to grow, and you're going to exit from the linear regime. What is going to happen? And this is not something that we can treat theoretically, so we resort just to pure numerical simulation. I'm sorry, it's not satisfying. So what we are plotting here is the mean square displacement for different instabilities. So we prepare the system, and we look at what are the eigenvalues, omega I, and we look at the mean square displacement. And then we consider another system with another dominating eigenvalues, just to explore a different range. And what you see is always the same pattern. So you see this exponential growth after a transient. So at some point, the unstable mode is going to dominate the response, and so you start having the exponential growth. Then the exponential growth, so this will be the linear response regime. At some point, it breaks down, and we see a kind of a plateau here. And then you will find a secondary instability, and the system jumps and starts entering a kind of diffusive regime. This is what we observe. So you have 3 times end of the linear response regime, end of a plateau regime in which the mean square displacement is not really changing much, and then beginning of a diffusive regime a later time. So how do we interpret this thing? So first of all, what does it mean that the system is described by the linear response regime? So the linear response regime, we get it looking at the eigenvalues. So it means that the eigenvalues are not changing. If the eigenvalues are changing, this is no longer true. So if we have a look here in the inset at, for one of these examples, at the imaginary component of the eigenvalue that are dominating the exponential growth, what you see well, they are really constant over the exponential growth, which is what you expect. Then at some point, something will happen to the system, and this is no longer the case. And what you see in our case is that these 2 eigenvalues are going to coalesce and become real, and then some mess is going to occur. And here I'm plotting the imaginary component of all the eigenvalues of our system. And what you see is that after this point, you have, in this plateau regime of the mean square displacement, you will have some complex eigenvalue, but then at some point you have a burst of complex eigenvalue. So the system becomes macroscopically unstable. You have a lot of unstable direction in phase space. How about structural changes? Again, these are the two timings. So what you can see is that these are the average number of contacts per particle. So what you see is that at the end of the exponential growing regime or the linear response regime, you start seeing some fluctuation. So essentially, you may think, okay, the system exit from the linear response regime when first there is some breaking of contacts. Before everything, it's okay. And you also see that you start having some contact that reach the Coulomb threshold. And then you see that when you have this macroscopic avalanche, you have a drop. And so the Z is decreasing. This is when the system enters the fluid regime. And as you expected, Z is smaller. And this is for the geometry. And for the mechanical properties, perhaps I can just comment on this thing. So this is the behavior of the pressure. So you can also show that the pressure is a similar exponential behavior with superimposed oscillation. You can get it. But what you see is that it's almost flat, the pressure during the growing and the stability. Also when the system has this plateau regime, but only when you have a macroscopic rearrangement, you have a change in pressure that drops. That's increased sharply. And similar thing for the shear stress, that it only drops. So the system is able to release the shear stress only when there is this secondary instability, which is quite large. So now I'm going to conclude with the last slide, which focus on the role of damping. What is this? The point is that we started these instabilities performing essentially simulation at constant NV simulation. We have solved equation of motion using equation of motion, but with no damping. So if you want to model any real grains in avalanche or earthquakes or whatever, there will be some dissipation. Dissipation because in contact between the grain, dissipation because there is a fluid, so there is dissipation. So the question is this dissipation destroying this physical picture or something is surviving? So this is what we have investigated. And how we have investigated, we essentially studied the instability adding some viscous damping to the grain. So in the equation of motion, there will be some minus gamma V to each particle. This is what we are doing. And this is the result essentially that we found. Essentially, if you study an instability, we know that we have a growth rate which is controlled by omega I. And then this is a time scale. And then you have another time scale, which is the time scale of dissipation. And so you find what you might get. So if the time scale of dissipation is larger, so you dissipate on a long time scale with respect to that of the growth instability, the instability survives, and this will be this case here. If instead you are dumping too quickly, you are killing the stability. So you will have in general a number of unstable modes, of imaginary modes. You may have, for a real system, you may have omega i's also very, very small, so say soft instabilities. And these soft instability are not expected to be strongly affected by the damping. So in this sense, the picture might be relevant for real situation. So to conclude what we have seen, first of all, we have seen that failure of the granular system is not, at least is not always related to this localized failure of a contact that is reaching the Coulomb threshold. We have seen that when you develop a coarse grain model of a granular system, you end up with a model which is not Hamiltonian. And we have seen that it is possible to describe formally the stability of the system, introducing this Jacobian, which is not a real matrix, and so you have this complex eigenvalue. And we see the interpretation. The interpretation is an oscillatory instabilities, and we have validated again numerical simulation. And essentially, what I'd like to stress is that this mechanism can be seen as a mechanism for the amplification of small perturbation. You have a small perturbation for deviation of mechanical equilibrium, and this one is amplified as one. So I've been told that each serious talk should end with a speculation line, which should be called actually the so-called bullshit line. So let's talk about some possible relevance, and the relevance that we're thinking of is for earthquake, remote triggering of earthquakes. So what you know is that sometimes you have an earthquake on a fault, and after some time you have an earthquake on a distant fault. So, and there is a correlation. So these two are communicating. How they are communicating? Of course, through seismic wave. So the first event is generated on seismic waves that are traveling, and they are hitting the second fault, causing the instability. But then seismic waves, after they move, they are actually damped. And the damping depends on the frequency. So high frequency waves, they are strongly damped. So they are not able actually to travel much. So the other fault is eaten by low frequency waves. And low frequency waves have a small energy content. So the problem is to understand how a small energy perturbation is actually able to trigger failure. And one possible answer could be this one. So what's happening is that the system is close to one of these bifurcation mechanisms. And so if you perturb it, you are just giving the go, and then the stability develops. Of course, this is below the bullshit line. We don't know precisely the truth. OK, so thank you so much for your attention. And this is, these are the people I've been working. So there is, since the first part of the talk is with when I was working in Naples with Lucilla, that many of you know, Eugenio Lipiello, and this other part on the theoretical interpretation is more recent work with Itamar, Oleg, and Joit in Singapore, that he has done most of the work.
I'm not sure I got your message, but so you say that these avalanches are triggered by some previous oscillations, but these oscillations are collective stuff, no?
These oscillations are collective stuff, yes.
Involving many, many particles.
All of them. All of them. Well,
but then you are connecting
with
the waves coming from the other ones?
So there is, wait a moment. So if you look, for instance, as this animation after some time, let's wait for the thing to develop. Okay, you can perhaps just see it here. So what you see is that, yes, these are trajectory of all the particles scaled. So what you see, all particles are moving, but you're going to see that there are particles that are have large displacement and particles that have no. So it is true that it's collective, but in a sense could be localized. So could be, the displacement could be dominated, is not even, the displacement is not the same for all particles. This is usual thing that also happen in usual normal modes. So all particles are moving in a mode, but the amplitude of the displacement of each particle could vary. So this is somehow the analogous. So it's collective. Everything is moving, but they are moving to a different amount. And so it could be that what will happen is localized. Here you have particles that are moving more, oscillating more with respect to the others. So what we see is that, yes, this is what's happening, say, in the linear response regime. Then what we observe, here we kind of make theory, is that, so this is, you see, the mean square displacement is very small. This is in the unit of particle diameter, 10 to the minus 7. So it's really, really a minor thing. But this thing is somehow the origin of a macroscopic failure. So start oscillating, oscillating, oscillating. Then in this case, you exit from the linear regime. You trigger other complex eigenvalue. And at some point, everything fails. And now you see the displacement starts to be of the order of 1 particle diameter.
But this oscillation is not exploded. Why it stops? This is something like you are doing artificially.
This is something that we observe. So this is out of the linear regime, so we don't know. So why we stopped, we have a clue. And the clue is, if you look at the modes, for instance, what you see is that the two imaginary modes collide. So the modes are originating from the structure, for the forces of the particle, right? So it means that the typical force, they are changing. And this is something that we link to the fact that you start having some change in the contact network. So the average number of contacts start fluctuating, or you see you have some contact that reach the Coulomb threshold. So the stability matrix is not constant over time because it depends on the particle position. Particle position starts moving with growing oscillation. As long as the particle position, the displacement of the particle is small, the displacement matrix, the stability matrix is not changing. So you are in the linear response regime, and this is the case. At some point, you move too much, and so the stability matrix changes. And in our case, we see, for instance, that the complex eigenvalue are coalesce. No, this is standard. No? Linear response theory is just the beginning of the exponential growth. Then at some point, something catastrophic may happen. So in this case, what's happening is that some contact breaks, and so the eigenvalue is going to change. And so there, we are not able to make any prediction. But what we see is that this appears to be a precursor of a macroscopic failure, where you see the displacement is of the order 1 particle diameter. This is what we see.
Where does the friction coefficient go?
Yeah, so
Where does it go into? I mean, so if you tune your friction coefficient,
if we tune friction coefficient, we see always the same. We don't see changes in the scenario. We don't see change. So it's not. So in this, yeah. So it just we will have another form for the interaction force when you smooth it out. So instead of having this thing, it's there. But it's not. We don't see any qualitative change in the behavior. So we also work with a very high friction coefficient, which actually is useful because it allows to.
how do you go from the frictionless to this frictional? Can you bridge this gap?
No, you cannot bridge. Why you cannot bridge? You cannot bridge because as soon as you switch on friction, you have this. But yeah, as soon as you have tangential forces, so you can put friction coefficient to infinity, so that there is not the Coulomb limit. It's not. This is what is causing the problem. What is causing the problem is this. This is the new physics. It's not the friction coefficient. If you add addition between the grain, I think it's not so. The new physics, essentially, as I was mentioning, is this one. So if the addition is not touching this, so it's not touching the tangential interaction, and the fact that the tangential interaction depends on the normal one, on the relative compression of the particle, I guess you still expect something similar.
So
because
you're renormalizing your addition into the normal force.
yeah. This is what you expect because you're touching the normal force. Because the new physics is the asymmetry. So,
Even I have a question.
yes.
The question was just that in this picture that you showed about this particle was exploring about its mean position, and some particles are moving more than other particles. Is it some kind of a delocalized mode that's traveling all over the place? And is it an analog of what people see in classes, the boson mode?
Well, it could be. It could be. This is the frictional case, yeah. So you can make, where we are doing this kind of study. So in a sense, yes, you can study what is the. No, first of all, those modes that you talk about, gases, they're always stable modes. So people somehow minimize the energy and then look at the perturbation. Here we're talking about modes that are unstable because they are complex, right? So what you can do, yes, you can do the same study, same sort of study, and you can see if the displacement field is localized or not, as the people do in the classic community. And what we see, I was mentioning, yeah, we see some degree of localization for the unstable mode. Yeah.
Is this similar to this short-net idea that these divergences are always accompanied by a oscillation?
Yeah. We don't know. We are thinking about this. And actually, we are also thinking that the same mechanism, which is related to this point, could be at work in the macroscopic interaction between surfaces. So the Coulomb friction coefficient between two objects is, again, if you want to develop a microscopic description between these, then you may actually end up in the same scenario. So when you describe the effective force between two surfaces, you have forces that are not coming from an Hamiltonian. So also how the slip of two surfaces, how the transition from the static to dynamic friction is taking place. So perhaps it's connected to this. But anyways, Sornet is not formalized in this way, so I'm not really sure
It's always saying that the divergences are accompanied by this kind
of the oscillation. Yeah. So perhaps there is a relation.
Okay, if there are no more questions.
Thank you so much.